charge carriers are polarized, you get a Hall voltage even without a magnetic field, and that's what this term is. And this is what's called the inverse spin Hall effect. If you have a gradient in the polarization, like in the lateral spin bulbs that I showed yesterday, you also get an electric current that's perpendicular to this gradient, essentially. So now, spin current, you can have the same kind of, just for, put it here for full, you have here the direct spin Hall effects. If you have an electric field, this is the spin current that you get from that. What is important to notice is that in all these terms where the electric fields and the spin currents, or the polarization and the charge currents, are connected, you have this term gamma, which is known as the spin Hall angle. And this tells you how strong the spin Hall effects are. And what this is it's the ratio of the spin Hall conductivity over the charge conductivity. It's a material-specific parameter. And so what does that mean? The charge conductivity, we know what it means, right? If we have a material and we apply an electric field to it, the charge conductivity tells you how much charge current you get. So it's essentially this thing here, right? This is how much charge current you get for a given electric field. Now the spin Hall conductivity tells you how much spin current do you get when you apply an electric field to a material. So what it is, it's this thing here, right? And it's easy to see, because this is the electric field, this is spin current, it's easy to see that if you divide this by this, you get gamma, okay? So now, it's important to know how big this number is in order to figure out which materials are useful for applications of spin Hall effects. So how do you do this? Well, it turns out in the early 80s, there were already some early measurements from Albert Fermi. So he thought about spin transport way before he did giant magnetic resistance. And what he did is actually a clever experiment. He took copper and they put manganese into the copper. And when you do that, what happens is that the current becomes polarized in the copper. And then they add additional impurities, let's say iridium or other ones that I can't read very well right now, lutetium and indium and what have you. And by putting additional impurities in there, they can change the strength of the spin Hall conductivity. And it can go positive, it can go negative. Very interesting experiment. And even then, they measured the spin Hall angle, for the example of copper with 0.2% iridium, that's about 2%. So it means that about 2.6% of the charge current gets converted into spin current. That's pretty good. So more recent, there are different approaches for determining